Hello, D.
Hi, Professor.
Okay, so you can hear, and we have everybody here except Yak. Okay. Okay, so let's get started today. This is Wednesday. Our week 12 lecture B. Starting from today, we are going to talk about feedback control. Okay. Yeah. So I already gave you problem set PS8. So I'm also trying to design a module for you to give a lecture on over the Zoom. So you choose some of the topics not covered in a class by going into the literature and focus on that and read and prepare slides and present. Okay. It's about 25 minutes each. Okay. So the final exam, perhaps we're doing the same thing as a midterm, okay? It's the in-class 90 minutes. So we talked about LTI systems and talking about necessary conditions, talking about BIBO stabilities, and I know the relationship to the impulse response. So starting from today, we are going to talk about feedback, different standard forms, and controllability, observability, and stability. And we'll see if I have time to do some exercise, but perhaps we don't have time, okay? For readings, 240 to 44, those feedback controls. So remember, we have a difference between state feedback versus output feedback. So usually this logic sequence is to learn state feedback, then output feedback. So state feedback, bear in mind, is just mathematical preparation for the output feedback. So in practice, you should not assume, you should say that not all states are measurable. Okay. Not all states are measurable. So some of the states internally simply is not observable. It's not physically, not, I should say, not physically, not physically measurable. Oh, I said, not all states are physically measurable. You don't need a not here, I'm sorry. Okay. So the idea is you have a system, you have a disturbance, and you give a command. So this is the command or reference. Okay. Give that to it. So you get output. Then you make, so this is your, I think this should be, the command should be called actuation signal. So you get output in here. So now remember we're talking about output. So when we say x dot is ax plus bu, y is cx. So if y equals x, then that's called a state feedback. But in general, it's not true. You cannot measure all states. So you have a C in here. You have C in here. And the dimension of y may not be the same as x. As you can see, c may not be a square. So that is something here. And remember, I talked many times about MAD notion. Modeling, you need a model of the system. So when you write this form, you are writing a model of the system. So that's the model part. And how we can get ABC, we're not going to put emphasis on that. That's a separate course. It's called system modeling or system identification. But to analysis like controllability, observability, stability, all these things is analysis. The design is basically talking about here, okay? How to design a compensator, put it here, such that the system output will behave as our references, okay? References. So the references is like we're saying, what do you want? So what do you want? I want my y at output as close to my reference as possible, okay? So what do you know? So giving A, B, C, how you come out this such that the system output will be. So all the control design part, you have two questions, okay? Two questions. What do you want? And what do you have? Or what do you already know? Okay. So that gave you a picture of why we need feedback for what, okay? But there's another hidden requirement that you have to guarantee the closed loop is stable, okay? And it's not only from in and out point of view, but also internally, okay? Internally, meaning there's nothing, there's no signal within the system that is not bounded. So you cannot say, oh, the in and out looks fine, but inside the system is unstable. Then you'll blow up the system as well. So we need not only input-output stability, but also internal stability. Okay, I think this is hidden requirement, it's a basic requirement. Otherwise, it's so this is necessary. So there are three types of inputs. Okay, so can you see that? So one is disturbance from here. But remember, the disturbance could be from here, could be from here. Okay, so in the front, it's called a load disturbance. In the after, it's not called load disturbance. It's called what? It's called output noise, output disturbance, like measurement noise, okay, like noise. So remember, we put in the front, in the middle, does not mean it's here or here, so it's just general, okay? So that's external reference, that's our command showing, answering the questions of what do you want, okay? What do you want? And commands, that's the actuation signal giving to the system. It's all, sometimes it's also called a control signal. Control signal. So concentrate in this course on commands. So we talk about U and Y, you know. So we don't do this a lot. So far we focus on not closed loop, but giving U, giving Y, and you have A, B, C, A, B, C. like state space, or you talk about GFS, or in a MIMO setting. MIMO is default, okay? When we don't say anything, everything is MIMO. And actually, there's another thing, so if nothing specifically said, is LTV. MIMO can be state space, can be IO, input-output model. So talking about state variable model ABC, so the controller is a compensator, like called state reconstructor, because I said state is not, the state X feedback is not possible. I told you, not always possible. So, but how we can make this one happen? So basically you have input, you have output, you also have the input signal. So these are U and Y signal coming out of here. So this is called OBS, observer. You're coming out an estimation of my X. Then you use everything you learn for state feedback. Okay, state feedback. So you need to have a reconstruction. So this is called reconstruction of X hat. Of course, I hope my X hat asymptotically will convert to XT, okay? As T goes to infinity. So asymptotically stable. This is aerodynamics. We'll show this later. So estimator of the state, and then you need to decide what's the gain feedback. State feedback, you put a gain in here, okay. To the state feedback usually is okay. So that's controller, we have two parts, okay, two parts. But today we are not going to talk about this observer, that's for next week, okay? So today we are going to assume that my Y equals X. So we can do state feedback. So we don't have this step. This step is for next week. So let's start. And of course, this is RTI. State is available that you can, Y equals X. So C is I, okay? Okay, C is I. State feedback means you have a reference in here, add to this U in here, but you also have a minus KX. So this is called state feedback, okay? State feedback. Okay, so do you guys believe this is right? Why we should not put another KR gain matrix in here? Why? Okay, I don't see any reason you should set the coefficient in front, that is I. So right now is I, right? So that's not really correct to me. Let's see. Yeah, let's see. We just have a reference in here, have K in here. So basically I have a U is my control, Y is X, C is I, okay. Giving this X, you have K times X. Now you do this way. Okay, that's correct. You put I in here, okay. Then you have this signal here and drive it, okay, drive it. So that's with this is a control structure, okay, control structure. So control design, usually you have first, what is the structure? Second is, what is the parameter? Control parameters or control gain matrices, okay? So when you talk a control, you should answer two questions. What's the structure? What are the parameters, okay? So in here we answered both, okay? So now what's remain to decide is the K. I don't know what is the K. So I need to choose this K such that, okay? Such that what? The overall system such that the overall system is stable, okay? And I hope the poles can be put in the places I want, okay? Pole locations, okay? Because the pole location will decide the system dynamics behavior, right? How fast it responds, and all those time domain transient behaviors, depending on the pole locations in the complex plane. So when we write this one, so we can see we have A minus BK, we have BRT. So, okay. So this is called closed loop state equation. Closed loop state equation. Okay. No question, right? So this is simple. But I hope you notice that this reference is giving, RT is giving, and B is also giving. And remember, we should have the question about is A and B minimum realization? Minimum? Is A and B is a controllable pair? Okay. So all these are the questions, okay? So it's not like arbitrary A-B combination will do all the work. That's not true, okay? Oh, let's move on. So let's say transfer function like this. So remember, in overall speaking, C is I. In this case, you don't consider this term, so you only have y equals x, so x is y. So it's Si minus A inverse Bu, okay? So that is something here. What is a transfer function? Transfer function is basically x of s divided by u of s, okay? Okay. All right, so remember that we are doing MIMO here, and so we need to be careful, and the writing of this way is questionable, okay? You should not write. So these are the two vectors, okay? Okay, so be careful, okay? So this is a matrix, it's a MIMO matrix. And you cannot swap their the position. So this is an open loop system, an open loop system without feedback. If we have feedback, so U goes to this is equal to X times K equal to UC is the control signal. And the UC, that control signal, okay, will feed back, and this one UC will get R minus this UC. I'll come back to this later. So this is called closed loop with this K, okay, from UC. So this is open loop. Well, once I have closed loop, then I have this form, okay, this form. So then what is the input? Input is this guy. So where instead of talking of X divided by U, I have X of S divided by R of S. Okay. So the whole thing will become like this. So compare this one to this one. I don't see anything changed except you have a BK in here. BK in here. B is giving and K is to be decided. Okay. Okay. So to decide the K, you have to tell us what do you want? What do you want to achieve? We'll answer this question later, but keep in mind, control is to address the question about, oh, what do you want and what do you have? What do you know? Okay, these two questions. But there are two more questions after that. Everything is done, then you have to answer two questions. One is how optimal, and how robust. So if you ask these two questions after everything is done, then you are at a much higher degree. So I think you need a dedicated course. It's called ME 212 212. Okay, 212 for answering these two questions. But let's focus on what we have here. And everything we have here, we call this is just nominal system. Okay, nominal system. Okay, nominal system. But in practice, A and B should have a range. It's not so accurate. So that's the topic for ME 212. So then if you have a C, then Y equals CX. So you will get this a closed loop system. So there's a summation in here. Of course, we derive the UC signal in here, so you get this. So US is R of S minus this. So you have this. So from U to R, from here to here. Okay. So this one has a special form. So this is a SIS. Okay. So this one inverse is here. Okay. Because we say this is U. Okay. So this whole thing is U. Okay. This is U. Okay. And U and R is converted from here. And this whole thing has to be the same as we derived before. We're using other derivation method. These two things will come up like that. Okay. So what? So if you have output, then you just add C times X. So X is this big one. Okay. So from Y to R, you can just derive it. I hope this is not very confusing. One thing a little bit confusing is how to convert U and R. Okay. So from algebraic manipulation, so this is interesting. This is true. This is true. So this can be proven. Okay, this can be proven. So we assume this is X. Okay? This side is X, and we also know this is X. Okay, so this is Y. So then we can pull out this one inverse, and this is X. So this is my X. Okay, this is X. Like we mimic to check this. This is true. Okay, this is true. If you need a proof, that's actually easy. So what do? You left multiply this side with this. So you got I plus XY times X. Okay. And you multiply this one both sides, you'll have X 1 plus YX. Okay. So you right multiply both sides with this, left multiply with this, So this to this, to here. So you get X plus XYX equals X plus XYX. So it's the identity, okay? So this is identity. So the reason is we never seen something like this, so y to r or x to r. We didn't see like that, so this is very strange. So we have seen something like this. I mean this whole thing we have seen. So then I'm showing you by doing that's this matrix identity, and this is called a matrix identity. So then we can write stuff like this, okay? Like this. However, we can group them because you have an inverse, I have an inverse, I can group them, right? So I can just multiply inside. So then this is I, this comes out. So you will get the same thing like this, okay? Something like this. So all this MIMO signal manipulation, just be careful about left and right multiplication. You need to be careful. So, so that's open loop, closed loop, that kind of manipulation. I hope this is quite clear to everyone. Let's see an example. Okay, Newtonian system with position P. You add a force. What is this? This is Newton's second law, right? So position double dot is U is my force. It's like ma F equals ma. Okay, and A is this guy is my ma, and this is F. Well, so but on the other hand, the Newton's second law is also called point mass. And also, if you should put the U in here, okay, and you put P in here, what you put here is this one. So you should have 1 over m, okay, right? Yeah. So basically, the point mass Newtonian system is nothing but open loop wise. It is it's a double integrated system. Okay. So if you see this one, you should immediately say point mass Newton's second law. Okay. So assuming that you are measuring the output, so and summation of the output and speed add together as a variable. Okay, it's measured. So what's the transfer function? Because this is position, this is velocity. So, and this is double integrator. Okay, that's my transfer function. And this transfer function, we can do realization. And so that is from in and out point of view. So this is basically is with a U of S, and this is Y of S. But Y of S is actually 1 plus S P of S. Okay, P of S. So x1, x2, so that's standard state vector. Let's just say there's unit mass, okay? So we're going to have something like this. So what's this one? This is nothing but the Jordan form, right? So Jordan form, we learned that the last column, last row corresponding to the B, if it is non-zero, then it's controllable. And its first column corresponding to C is it's not zero, then that's This is a SISO system, isn't it? Yes. So then it is. So this system, we can see this ABC is both observable and controllable. Okay. Okay. But remember the output here. So I have a. So this is a x1, x2. So x1 is position, x2 is speed. Okay. So say for example, I'm only measuring speed. I'm not measuring position. Then we are going to see this system is not observable. Yes or no? Mm. So without measuring speed, position is a troublesome. Okay. So state feedback means I have a reference RT. So basically, I'm saying I have is written as minus kx. So x is x1, x2. K will be the k1, k2, x1, x2, like that. Okay. So this is like 1 by 2. There's a 2 by 1. So that's why U is 1. So. So that's the structure of my controller. I'm doing state feedback, and yeah, we write this way. Yeah, it's the same thing. Then closed loop system will be B minus is a A minus BK. Okay. Okay. So remember, B is 2 by 1, K is 1 by 2. That's why you have 2 by 2. So that's why in the end you have originally 0, 0, 0 is A. Okay. After you have done, you have A minus BK here. Okay. That's BK. We didn't have any change in here. There's a C in here. So actually, this looks like a control standard form. Okay. So that's a closed loop state space. Well, if we do a closed loop system, so you didn't do anything here, okay? Be careful. I didn't do anything in the numerator, but I only changed the polynomial in there. Previously, you only have a s square, but now you have this. So this one says, so remember, I call M, S, D. Mass, spring, damper. Okay, so I hope you understand. In this 3 term, this is due to mass. This term is due to damping, okay, damper. And this K1 is due to spring, okay. So it's like you have a point mass, okay, you have point mass, okay, you have point mass. You have point mass, and you have a U dragging going forward, and you don't have friction here. So this mass will move according to Newton's second law. Once you add the U of t, you'll keep going. We'll keep going, okay? You are not going to come back. You just keep going to infinity. But on the other hand, here you have a spring hook up with this, and you also have a damper hook up with this, okay? So then the system could potentially be You drag this one. Once you remove this U, it will come back to the equivalent point. Okay. So that's the interpretation. So in other words, by introducing this K, not 0, you basically can change the system behavior, including its internal behavior and in and out behavior as well. So that's the beauty of the state feedback. You can change it. But the question is, can you arbitrarily change the behavior? Okay. So that's the question we need to ask. So it can affect the pole location because K1, K2 can be choosing arbitrarily, okay, because of that. So the pole position can be located. So it's called choosing K1, K2 for pole placement. So for the ABC system, somehow you can make the pole of the A matrix change to the desired position. This process is called pole placement. In the future, I'm going to use PP, pole placement. And nothing changed in the 0, okay? The 0 cannot be changed via state feedback. So if somebody say they can do it, that's a lie. You cannot. So then, so the question is, can we do 0 placement? Good question. My answer is, I haven't seen a systematic method to do that yet. So it's a topic of research. You can Google this term to see what you can have. I can find 0 placement. I don't think so. I don't think so. Okay. So it's possible you can choose K1, K2 such that it is pole can be coincident as my 0, so you can cancel out. So the closed loop state variable model may not be minimal. So after you have choosing the K, so you have a system A, B, C. So after you have choosing the feedback control, it becomes A prime, B actually didn't change, okay? I see, so you only changed A prime. So this one could be minimum realization, but the whole thing after that, because of a pole 0 cancellation, it may or may not, may and may not be minimum. So this is something you should observe, okay? Because of the cancellation of 0. The pole can be arbitrarily placed. Realigned with the 0, it can be cancelled, okay? So will the state feedback affect my controllability and observability? This is also a quite fundamental question, and whether it will affect stability. As you can see, the answer for this one is, because you are placing the pole arbitrarily, you could mess up the system to be unstable by putting the pole in the right half plane. So what we can do is the state feedback, okay? And so already we answered that. We can place the pole. What if the state is not available? Then you have to use observers to reconstruct an estimated, it's called estimate. Observer can be also said state estimator. You estimate X hat. Okay. So here are these answers to the questions. If the closed loop system is controllable, if and only if the open loop system is controllable. So the controllability property is never changed during the feedback. Okay, the Hautus test is something like this. So right now, yeah, because okay, so this is open loop, right? So closed loop is actually Si minus A plus actually BK. Okay. Then you have another B. So check the rank. Basically, you have this multiplied by this. So this is the full rank, will not affect. So the rank is the same as this. Okay, that's beautiful, isn't it? This argument is beautiful. Okay, so obvious. So whenever you see this obvious, that means it may not be obvious to you. Okay. So also there's when you read the paper, if you say something somewhere say apparently or obviously, you need to be careful. Usually it is not. Okay, so open loop controllability and the closed loop controllability will never change. If I want you to give a talk or give a proof, you should be able to argue it in a very simple ways in this Hautus test about the rank. Okay. Okay. If you already, the system has some uncontrollable, it's not a minimum, okay? So you have uncontrollable eigenvalues. So if it is not controllable, okay, this eigenvalues, we talked about model controllability. If we forgot controllability, if you forgot this one, go and check it, okay? Including those very complicated Jordan blocks, okay? So the rank didn't change, okay? Rank didn't change. So after feedback, those uncontrollable eigenvalues, they remain uncontrollable. Okay, that's very important. Okay. In other words, feedback will not change the fate of the controllability. So if you don't have something not designed well and it has something not controllable, then you do some feedback and use some smart ideas. You will never make it controllable. You have to throw away the system and rebuild another one. So controllability is a fundamental defining physics feature of the system. You cannot change via your smart feedback control, whatever. So if that mode is not controllable, no matter what you do, you cannot change that fact. It's fatal. It's fatal. So if you have something not controllable, the message is don't try to control it. Isn't this so simple? Because it's not controllable. So, but in math language here is so obvious. And same thing for observability. Okay. So yeah, you can factor this one out. Then this is totally not possible. So observability may lose. So you have this case, the system is no longer, but controllability is preserved. Okay, controllability is preserved. So because of this cancellation. So okay. I don't like is. I prefer may not be preserved. Okay, it's just a possibility. May not be preserved. It's better. Yeah. So let's run a few examples, and then we can stop and ask some questions. So, so let's see. This is A, B, C. So we are having what are we doing here? So this is a MIMO system. It's 2 in, 2 out. It's a 2 by 2 system. But internal state vector size is 4 by 4. And this is LTV system because of this thing. So you do CB, C1B, C2B, interval says the B is not 0. One has a constant relative degree. Do you guys know what is the relative degree? I think at some point I explained it. I think we explained the relative degree when we talk about Markovan parameters.
Is it the difference between the polynomial on the numerator and denominator? Or...
Yes, for the G of S, that's true, but that's for SISO. But for MIMO, how we decided. Okay, so let me do one more time here. So we're talking about this one, okay? So if I have a DU here, okay, so this is called relative degree 0 because U explicitly contain an output, okay? So what if I do derivative? Okay, so we don't have this one. Okay, suppose we don't have this one. Okay, I do derivative. I'm going to have CAX plus CBU. Okay, so then I will see that if this is 0, then that means Y dot does not contain the U at all. So this is not relative degree 1. So you have to do Y double dot, just check. So you have a CA square, okay, X plus CAB, C, okay, well, X, to the X dot. So this is already 0. You got CABU, okay? If the CABU is still 0, then keep doing it until you see double 3 dot CA square cube X plus CA square BU. So you see some patterns in here, So you do the derivative until you see this is not 0, okay? Okay, not 0. And then this is called a relative degree 2. Okay, relative degree 2. Okay, so this is not 0. It's 0, but it's third degree of derivative is not 0. Then this is called relative degree checking. So this is basically the check that. Okay. And the relative degree sometimes, because it's LTV setting, okay, LTV setting, and that's dependent, it could be time dependent, okay, depending on the time. So it's quite complicated when we talk about relative degree itself is not constant. Okay. So I have a kx plus br, non-interacting closed loop state equation is like this. So you can introduce this state feedback, okay, state feedback with time varying gain, time varying here, and substitute. So this is our closed loop system, and it can make the closed loop system in this LTI, okay, LTI. Okay, so this is kind of more interesting to eliminate the BT effect here. So by introducing control, feedback control. So just let you know that in the LTV case, there are more things there, including the relative degree is time varying. Let's go to another example. Of course, you have this is a controllable form. This is a controllable form. Okay, so this is identity matrix, and then this is observable. Okay, so this was developed in the previous chapter 2. Nth order linear differential equation given by degree n polynomial. So degree n. So this lambda, okay, I hope you understand what's going on here. This lambda is just a symbol to show DDT, okay? Show the DDT. B is not 0 for all t. So what you do, you make the control signal like this, and you replace all these coefficients in here, okay, in here, and this is the state feedback. Remember, original system coefficients are time varying, but I copy them in here, and then I want to make the overall system to behave like this closed loop characteristic polynomial like that. So that's why I insert everything here. Remember, this one will cancel out this one. You can see it cancels out. And the most important thing is this B0 is in the denominator. Whenever you put it here, it will cancel out. Okay, it will cancel out. So then in the end, again, LTV becomes LTI. Oh, no. LTV becomes LTI. Okay, LTI. So you feel this is a magic. Actually, I want to say something more about it. If you have a nonlinear system, okay, not just time varying. It could be time varying, okay? It could be time varying nonlinear system. remember, we actually discussed the time-varying linear system, okay? We can convert to that through a time-varying state feedback, okay? But I am telling you that it is possible for time-varying nonlinear system also through a state feedback law like this, okay? Similar to this, okay? You can turn the nonlinear system into LTI system. This one is called nonlinear systems feedback linearization control. So feedback linearization is to introduce a nonlinear feedback law, nonlinear time-varying feedback law to turn the general time-varying nonlinear system into a LTI system. LTI system. So that's called feedback linearization. And this overall general situation is within ME-211 nonlinear control course. Okay. Next offering is I offered 2018. So next one is 2021. Okay, next year. Yeah, next year. Yeah, 2019. I offered this one is ME-212 robust and nonlinear control, robust and optimal control. So 2020, so ME-280. Okay. So then we are going to rotate. So there's 3 high-level control courses I developed here will be rotated every 3 years. Okay. So next semester I'm teaching this course, and if you miss, you probably will miss forever, because next time I offer it, you probably already graduated. So you should consider to take it. So here are other examples. So here we are extending some concepts for feedback. Okay, you can see feedback can do way more, not just for pole placement. Okay, feedback has limitations. You cannot change the position of the 0. We have known that. But here I'm showing you by 2 examples that feedback can turn LTV into LTI. Feedback could turn nonlinear into linear. Okay, so maybe I should do it here. So actually, everybody remember we have Earth satellite of unit mass with this model. The R double dot is this minus this plus U1 is the propeller, and the angular acceleration theta double dot is something like this. Okay, so you have a U2. It's a 2 components. U2. So it's a 2 input, 2 output system. Okay, you have R and theta. And at a certain point, we remember we run an example to see this one as controllable or observable, and based on which one you measure. So measure theta or measure R, or measure theta dot or R dot. That will change your observability conclusion. So we went through that example. So let's go through this one more time, and you have initial conditions in here. Then you do linearization. So these are nonlinear system, okay? But so these are the nonlinear system, very nonlinear, okay? Very nonlinear. But if you assume the initial conditions, okay, though these are initial conditions, then you have some nominal solutions as so this the theta nominal will give that. So you basically, I hope we can linearize the system around the nominal system. Okay, so around the nominal system. So then we just do linearization around nominal solutions. Okay. So after that, we end up with a LTI system with this ABC. Okay. So we discuss about observability, controllability questions in here. So everything here is controllable. Okay. So we can generate those forces on the satellite depending on the states. So deviations will be dampened out. So this is, I'm hoping to design a state feedback control, all these matrices to satisfy some of the desired properties. That's, we hope to add some damping in there, like I showed you in the mass, double integrator, point mass Newtonian system. So by introducing all those K's inside, the K will be inside here. And then what are the strategies to choose the feedback gain? So you can see there are just so many, there are some 8 possibilities of choosing them. So there are several strategies so that the closed loop is exponentially stable. Indeed, to place the eigenvalue at desired location. So this is nothing but pole placement. Okay. So it's possible we choose some of the components are 0, some of the components are here. This is just by observation. Then we end up with a system with we have 2 triangle metrics, okay, like that. By doing that, we see we have 2 modes. One is here, one is here, okay. So you have 2 terms. The one correspond to this guy correspond to that. So this type of design by observation is still try and error. I don't like that. So try and error. However, by observation, try and error, if you bring in physical insights, that is okay. Okay, that is okay. Especially in this case, they purposely made some assumptions. So K21, this one can be 0. They did the K23, this can be 0. This also can be 0. So then they have a block diagonal type of thing. So that will make the design easier, okay? But this is not the way we want to go. I just tell you that the state feedback, you can bring physical insights when you choose those gain metrics. Okay, state feedback. We talked about state feedback concept, and we did the interesting matrix identity. So I hope that is fun. We using Hautus test that state feedback does not affect controllability. However, this could affect observability. Okay. In other words, the state feedback actually could make pole zero cancellations. Okay. And we showed two examples like LTV through feedback could be LTI. I know I keep doing this. LTI. We also did that LT nonlinear system, time varying nonlinear system could also go to LTI. And this is called feedback linearization. This is a popular design method, okay? So the idea looks like, if we go back here, the idea of feedback linearization is to, like in here, you can see, it is to cancel out those bad guys, you know? We can cancel out this one, becomes 0, right? So in other words, in ME211 course, we are going to, we are going to say that some of the nonlinearities might be good, could be good. Okay, could be good. Okay, could be good. Say, for example, you have a system x dot is minus lambda x. So you say, oh, this is a exponentially stable system. Isn't this nice? Sure, it's nice. But if somehow I have a ability to change the system, say, so I have a cube in here. So why should I cancel out the cube and replace with this? You know. Do you see my point? Okay. So next time we're going to learn some deep formulas. Okay, deep formulas regarding pole placement algorithms. There are algorithms. So in my lab, the corresponding traditional algorithm is called Ekman algorithm. Okay, but later people discovered Ekman has some problem, some issues. I think now people is not talking about this anymore. But when I was a student, it's a big deal. People always try to pick up Ekman pole placement algorithm has some hidden issues. But in my lab, I think in my lab, the command is called place. Okay, you can help place to check out what's in there. So that is as a linear multivariable control course class member. This is called bread and butter. Okay, you should be able to explain what's this and perform this design. You know, of course, it's a MIMO. Okay. So that is the first part. The second part, we are going to talk about observer. Okay, you have state reconstructions and estimations and so on and so forth. But now I need to have alert for you. Sometimes you say, oh, X, you cannot do that. So you estimate it. So this is called full state observer. Okay, so you construct all of them. None of them is available, okay? But what if we have partial? You have some of them available, some of them are not. So it's called a partial state observer. But academically, they don't use this partial. They don't like this. It's too oral. What do they say? but reduced order. Reduced order state observer. So this part is also important because you already can have some of the X observable or measurable. You only have remaining several of them not observable. So why bother you reconstruct all of them? So that's not right. So you should use whatever you already have. So you only reconstruct those partial unmeasurable states. So both scales are important for observer designs. Okay, and so this is just symbolically math is intense, but not hard. Okay. So don't miss next lecture. It could be very important because these contents are considered as a key competency. So in other words, if you never take this course and you start to read this part, I don't think there's a way you can catch up. So it's very hard to catch up. So we have a few minutes. Do you guys have some questions? Again, we are recording, so we are going to upload this one. We did this lecture, we did this ME-210 from beginning to the end. We didn't miss anyone, it seems. There's a good collection, right? So Yak, everything's okay? Oh, we have Carlos here. Hey, Carlos.
How are you?
You have learned all the stuff before or not?
Yes, some lecture I studied before, but I am
Refresh your memory.
yeah.
I see.
Something about memo system is first time that I see in this point of view. But
yeah, so I want to invite you to give us a talk in the end about your Phelps system, pixel heating system.
oh,
So
okay.
show them this is a real MIMO system. How many inputs?
16.
How many outputs? 16. So
yeah.
you have 16 by 16 and
yeah.
your VS.
256.
You have GIJ, you have 256. And the guys and Carlos made all the step response for each element, and he's going to construct that huge matrix. And also you present in a digital twin framework, okay? So
yeah, that is the idea.
So for Dee, Howie, and Jack, and Kevin, I'm going to give you some guidance about what topic you should choose, or I suggest you to choose. Then you present to make linear multivariable control more fun. But now, right now, it's like linear multivariable control is like, let's say Bible, no? It's a very fundamental course. All the control graduate students, you want to do control research, you need to have a very solid linear control system foundation like this. So you guys survived so far, and actually have my respect. So great. All right. Any other questions you want to ask me, Kevin? Looks like you want to say something.
No.
Okay. If not, I'm counting 3, then I'm going to end the meeting, and I will see you next Monday. Okay. 1, 2, 3. Bye-bye.
All right.